Class, I hope that you're surviving. I know this is really moving quickly for you, and I know that this is not an easy class for a lot of you. Um, if you have any questions about anything, of course, shoot me an email or give me a phone call. Let's see if we can help in any way possible to make this class successful for you. I'm going to do a brief video right now on Chapter 5 in your textbook, which is all about the normal curve. You've already gone through Chapter 3 on measures of central tendency. You've gone through Chapter 4 on measures of dispersion, the standard deviation, the range, the variance, etc., etc. And as you can see, I hope, in a statistics course, every new topic is heavily grounded in the previous topic. So it's like building a house. So if you don't know the platform before, the whole house is going to cave in. So it's important that you don't move ahead without fully understanding what you just went through or what you just worked on. This chapter is based on the normal curve. And now in school you've heard an awful lot about curving scores and so on and so forth. Well, when I started teaching statistics years ago, I realized how misunderstood this concept really is and how important it is as well. I'm looking now at page 123 in your book, which has a picture, figure 5.1, of a normal curve. It says scores for a group of males. These are IQ scores. The presumption about IQ scores is that they're normally distributed. What does that mean, normally distributed? Normally distributed means that there's a perfect shape of a bell, that most of the people fall in the middle, and an equal number fall on the right side and an equal number fall on the left side of this curve, the theoretical normal curve. It exists in theory, not in reality, but we presume normality for certain distributions that are explained to us in this chapter. So IQ scores are presumed to be normally distributed. So if you're looking at the book and you see that the IQ score right in the middle of 100 is right at the peak of that curve. Now in a perfectly normal curve, which again doesn't exist in reality, theoretically it does, that highest peak would be the mean, it would be the median, and it would also be the mode, right? The mean would be the average of all the scores, would be the highest peak. The median, which would be the score where half the scores fall above and below, that would be at the peak. And the mode would be the most common score, and that would be at the peak. That mean, median, mode, as you'll recall, are the three measures of central tendency, or three different types of averages. If you look above figure 5.1 in your book, you'll see the little table, males and females, and it'll tell you that the mean, but that's the X with the little bar on it, IQ for the men is 100, the mean IQ for the women is 100. You'll also see that the little s, which means the standard deviation for the males, is a 20, and the little s, or the standard deviation for the females, is 10. And you'll see that n, which means the number of males and the number of females, n, is 1,000 for both groups. Now there's one number that's different in that table, and that is the standard deviation. And by now, because you read the previous chapter, you should realize that the larger standard deviation is going to mean that the scores are more spread out, and the smaller standard deviation is going to mean that the scores are not as spread out. They're going to be not as dispersed. They're going to be clustered. Okay? So if you look at this normal curve down at the bottom, and then you'll see on figure 5.1, you'll see a line across the bottom. This is the first time we're being introduced to what I'll call standard deviation scores. You'll see the 0, the +1, the +2, the +3, the 0, the -1, the -2, and the -3, right? And by the way, what that means is when you convert, which we will learn how to do, when you convert the IQ score of 100 into a standard deviation score, which by the way is also known as a z-score, that's going to be 0. And when you convert one standard deviation above that 100, which is the score of 120, right? When you take that 120 and convert it into a standard deviation, it's going to convert into a +1 standard deviation. And then if you take the 100 at the mean and you add 2 standard deviations for the males, which would be 20 plus 20, that's 140, and that's going to be a standard deviation score of 2, right? That's going to mean something in a moment. I'll tell you a little bit about what it's going to mean right now. So in any normal curve, for example, the area between the mean, which is 100 or 0, whichever score you want to use, right, and one standard deviation above the mean is always going to be about 34%. It's actually going to be 34.14%, I believe. We'll check that out in a moment. And it's going to be the same on the left side from the mean to the first standard deviation. Okay? So let's continue and see if we can understand this. Now on the next page, figure 5.2, you can see that the figure 5.2 is the IQ scores for the females. That curve is more narrow, isn't it? Has a not as much spread. It also, though, has standard deviation lines that you can see that line right underneath all of the scores, right? The mean is 100, just like for the males, and when that's converted into a standard deviation score or a z-score, it's 0. Now, though, if you look back at the table on the previous page, you'll see that the standard deviation for the females is 10, right? And if you add 10 to the 100, you get 110. So the first standard deviation here is between 100 and 110. On the previous page, the first standard deviation was between 100 and 120. Notice that difference. What's interesting, though, is that the distance, or the area under the curve, that's between 100 and 120 for the males, and the area under the curve that is between 100 and 110 for the females is the same. 34.13% of the area under the curve. Even though it's more scrunched up, more clustered, the same area, the same percentage of the area under the curve falls between 0 and 1 standard deviation above the mean. Keep in mind that since these curves are symmetrical, which means evenly balanced or not skewed, we had that in a previous chapter, because these are symmetrical, what we're talking about with the right side from the mean to the first standard deviation also applies for the mean to the -1 standard deviation. -2, -3 is the same as -2, -3 on the positive. I mean, it's +2, +3 on the positive side. Okay. Now there's a neat table, a very handy table on page 124. You'll see it. It tells you. It says between and lies, that's the heading on the table, but it tells you without having to look things up what the area under the curve is between a -1 standard deviation and a +1 standard deviation. What it's telling you in that first line of the table is that 68.26% of the area of the curve falls in between -1 and +1. Now remember, I said between 0 and +1 is 34.13, excuse me, right? And between 0 and -1 is 34.13, correct? So if I add 34.13 and 34.13, both sides of that curve, I'll get 68.26%, which is what is being shown to you in figure 5.3 on page 125. Now, by the way, if you'll look also at that table on page 124, you'll see negative and +2 standard deviations encompasses 95.44% of the curve, and -3 and +3 standard deviations of a curve encompasses 99.72% of the area under the curve. Now, I keep saying percent of the area under the curve, and that means it's that percentage whether the curve is very narrow, in which case the standard deviation is very small, or very wide, in which case the standard deviation is very big. Okay? That's really important. I'm going to cut this video off here and try another one because sometimes the longer videos don't publish very well.